Okay, we continue. All right. We're moving on to question 7. And question 7 says or asks, in degrees, how much does the line current lag the line voltage? Okay. Now, if you remember this, this talks about the angle theta with the voltage that begins to rise before the current does, and that's because this is a lagging system because it's an inductive system. Okay, so if this actually this is the power factor we're talking about now. All right, so power factor. Okay. Uh, some definitions for power factor. We'll call it PF. One of the definitions we can work with is real power divided by apparent power. Okay. Another definition is that power factor is equal to the cosine of the phase angle, and that's the angle between the voltage and the current in our electrical system. Of course, we don't want to have to write phase angle every time, so we say that's equal to the cosine of angle theta as such. Okay. Okay. Now then, let me look around here for a second. In problem number 2, we found that we got the shaft power. Okay, I don't think we've done this yet. Hold on just a second. Okay, so here we are right now. Now let me digress here just a little bit. Here's our nameplate. We know the shaft power because we've got it right here, right? The apparent power we calculated, okay, when we were trying to come up with a current being drawn by the motor in a locked rotor condition. Okay, so we calculated that. But what we have not determined is what the real power is, okay? Remember, we have shaft power, and that's what the motor puts out. And when you talk about shaft power, you're finished with your conversation usually. Okay. But how much power in electricity are we bringing into the motor? Okay. Well, what we have to work with here is we've already seen that we have our apparent power. Okay. And we can let me just talk for a minute here, okay? I've got on the nameplate the efficiency of our motor, okay? That tells us how much of our electrical power, our real power, is actually getting to the shaft. So 89.5% of our real electrical power is getting to the shaft. We lose, 10.5% through a bunch of items such as friction, windage, that's the moving of air, inertia, starting, stopping, eddy currents, hysteresis, etc., and the list goes on. Right now that's not important to us because we're not motor builders. All we want to do is get a decent job working with nameplates. Okay, so we'll step right down here for just a second, and let me get a different color. And let's note that in the nameplate, our efficiency, I'm going to call it EFF, is equal to 0.895. That's 89.5%, right? Okay. So, and we know that this is equal to power out, power that we get out of the motor, divided by the power coming in electrically. So, in order to calculate our power factor, we don't know the phase angle, so we can't do anything. We know the apparent power. We don't know the real power, but I have a method by which I can determine that. And this power in, the electrical power into the motor, that is the real power. Okay, so that's what we want to determine. So what I can do is rearrange my equation, and I can say that power in, and that is my real power we're talking about, is equal to the power out, that's the shaft power, divided by the efficiency. And the power out, and we did this a while ago, right, was that's equal to 2238 watts. Okay, the efficiency is 0.895. And so my power in, and I just happen to have a calculator that I finally found here. I'll turn around here and get it. Is equal to 2500.5 watts. So my real power, my real electrical power, is that right there. Now I don't think we've done anything to see that number up until this point, but I had to know that before I could go any further with that. In fact, I'll go ahead and confess to you that on this little quiz that I'm giving you, I've got 7 and 8 reversed in order. If I had them in order, then this would fall into place naturally for you. Okay, so you have that. Well, you may have it, but you can't see it. So I'll lift this up, and there's the real power. Okay. I'll make a note of that real power. I'll get my trusty eraser. And now we can come back to work at the top of this thing. So, my power factor is equal to my real power, which is 2500.5 watts. And it does not matter which voltage we use. Okay, so I need my apparent power. How much room do I have here? My voltamperes will be equal to the square root of 3. Okay, let's use 460 volts. I'm multiplying here. Times 3.9 amps. Okay. Okay, so that number came out looking okay. So my apparent power is 3,107, and that's going to be voltamperes, by the way. This is my apparent power, and I'm going to put it right over here because we need to use it in this equation. And I get 80.5. So my power factor is equal to 0.805. Okay, now we can call that 80.5%, while we're chewing the fat with somebody, but when we get ready to do math, okay, then we have to use power factor as a decimal, and you'll see why here. Okay. All right, so there's number 1, number 2. Okay, and then so I've got two relationships for power factor is what I've got. All right. So we now know that power factor is equal to 0.805, and that is a good number for trigonometry. So we will say that cosine of an angle, theta, is equal to 0.805. And then if I want the angle, then I have to take the inverse cosine of that number. That. And if I have my calculator set in degrees, now what I'm getting here is I'm getting 36.4 degrees. Okay. With that, I can say that my current lags voltage by 36.4 degrees. So what I've done, I've just worked both problems 7 and 8, okay, in one maneuver because I actually had them backward. If I had any sense, I would have given you number 8 first, followed by number 7, and then this would be natural, and I wouldn't have all these arrows and what have you. So take a look at that, see what you think, and try, hopefully you'll understand it, and you'll handle it very well.